Prepare to be swept away by a cosmic symphony that reverberates through the fabric of space-time itself. In this captivating video on gravitational waves, we dive into the mind-bending realm where massive objects dance and collide, sending ripples of distortion rippling across the universe. Brace yourself for a sensory feast as we unravel the untamed power of these invisible cosmic messengers, illuminating the most violent and cataclysmic events in the cosmos. Get ready to witness the invisible hands of gravity composing a cosmic orchestra that transcends time and space, captivating both the mind and the soul. Gravitational waves. Gravitational waves are waves of the intensity of gravity generated by the accelerated masses of an orbital binary system that propagate as waves outward from their source at the speed of light. They were first proposed by Oliver Heaviside in 1893 and then later by Henri Poincaré in 1905 as waves similar to electromagnetic waves but the gravitational equivalent. First discovered, gravitational waves were later predicted in 1916 by Albert Einstein on the basis of his general theory of relativity as ripples in spacetime. Later, he refused to accept gravitational waves. Gravitational waves transport energy as gravitational radiation, a form of radiant energy similar to electromagnetic radiation. Newton's law of universal gravitation, part of classical mechanics, does not provide for their existence, since that law is predicated on the assumption that physical interactions propagate instantaneously at infinite speed, showing one of the ways the methods of Newtonian physics are unable to explain phenomena associated with relativity. The first indirect evidence for the existence of gravitational waves came in 1974 from the observed orbital decay of the Hulse-Taylor binary pulsar, which matched the decay predicted by general relativity as energy is lost to gravitational radiation. In 1993, Russell A. Hulse and Joseph Houghton Taylor Jr. received the Nobel Prize in Physics for this discovery. Speed of gravity. The speed of gravitational waves in the general theory of relativity is equal to the speed of light in vacuum. Within the theory of special relativity, the constant c is not only about light. Instead, it is the highest possible speed for any interaction in nature. Formally, c is a conversion factor for changing the unit of time to the unit of space. This makes it the only speed which does not depend either on the motion of an observer or a source of light and/or gravity. Thus, the speed of light is also the speed of gravitational waves, and further the speed of any massless particle. Such particles include the gluon, carrier of the strong force, the photons that make up light, hence carrier of electromagnetic force, and the hypothetical gravitons, which are the presumptive field particles associated with gravity. However, an understanding of the graviton, if any exist, requires an as-yet unavailable theory of quantum gravity. In August 2017, the LIGO and Virgo detectors received gravitational wave signals within 2 seconds of gamma-ray satellites and optical telescopes seeing signals from the same direction. This confirmed that the speed of gravitational waves was the same as the speed of light. Effects of passing. Gravitational waves are constantly passing Earth. However, even the strongest have a minuscule effect, and their sources are generally at a great distance. For example, the waves given off by the cataclysmic final merger of G-Galgi 150,914 reached Earth after traveling over 1 billion light-years as a ripple in spacetime that changed the length of a 4 km LIGO arm by 1,000th of the width of a proton, proportionally equivalent to changing the distance to the nearest star outside the solar system by 1 hair's width. This tiny effect from even extreme gravitational waves makes them observable on Earth only with the most sophisticated detectors. The effects of a passing gravitational wave in an extremely exaggerated form can be visualized by imagining a perfectly flat region of spacetime with a group of motionless test particles lying in a plane, the surface of a computer screen. As a gravitational wave passes through the particles along a line perpendicular to the plane of the particles, following the observer's line of vision into the screen, the particles will follow the distortion in spacetime, oscillating in a cruciform manner, as shown in the animations. The area enclosed by the test particles does not change, and there is no motion along the direction of propagation. Properties and behavior. Energy, momentum, and angular momentum. Water waves, sound waves, and electromagnetic waves are able to carry energy, momentum, and angular momentum, and by doing so they carry those away from the source. Gravitational waves perform the same function. Thus, for example, a binary system loses angular momentum as the two orbiting objects spiral towards each other. The angular momentum is radiated away by gravitational waves. The waves can also carry off linear momentum, a possibility that has some interesting implications for astrophysics. After two supermassive black holes coalesce, emission of linear momentum can produce a kick with amplitude as large as 4,000 km/s. This is fast enough to eject the coalesced black hole completely from its host galaxy. Even if the kick is too small to eject the black hole completely, it can remove it temporarily from the nucleus of the galaxy, after which it will oscillate about the center, eventually coming to rest. A kicked black hole can also carry a star cluster with it, forming a hyper-compact stellar system. Or it may carry gas, allowing the recoiling black hole to appear temporarily as a naked quasar. Determining direction of travel. The difficulty in directly detecting gravitational waves means it is also difficult for a single detector to identify by itself the direction of a source. Therefore, multiple detectors are used, both to distinguish signals from other noise by confirming the signal is not of earthly origin, and also to determine direction by means of triangulation. This technique uses the fact that the waves travel at the speed of light and will reach different detectors at different times depending on their source direction. Although the differences in arrival time may be just a few milliseconds, this is sufficient to identify the direction of the origin of the wave with considerable precision. Gravitational wave astronomy. During the past century, astronomy has been revolutionized by the use of new methods for observing the universe. Astronomical observations were initially made using visible light. Galileo Galilei pioneered the use of telescopes to enhance these observations. However, visible light is only a small portion of the electromagnetic spectrum, and not all objects in the distant universe shine strongly in this particular band. More information may be found, for example, in radio wavelengths. Using radio telescopes, astronomers have discovered pulsars and quasars, for example. Observations in the microwave band led to the detection of faint imprints of the Big Bang, a discovery Stephen Hawking called the greatest discovery of the century, if not all time. Similar advances in observations using gamma rays, X-rays, ultraviolet light, and infrared light have also brought new insights to astronomy. As each of these regions of the spectrum has opened, new discoveries have been made that could not have been made otherwise. The astronomy community hopes that the same holds true of gravitational waves. As we reach the captivating finale of this mesmerizing odyssey into the realm of gravitational waves, we stand in awe of the cosmic symphony that reverberates through the fabric of spacetime. These ripples, born from the most violent and cataclysmic events in the universe, carry with them the whispers of colliding black holes, the echoes of merging neutron stars, and the majestic dance of celestial bodies. With each detection, we unlock a new chapter in our understanding of the cosmos, peering into the invisible tapestry that binds us all. If you found our video informative, kindly subscribe to our channel so you won't miss out on our videos.